Hello, friends. Welcome back to You Can Do TV. The Panama Canal lifts a 325-meter cruise ship 26 meters above sea level using nothing but water. At IJmuiden in the Netherlands, crews built the largest sea lock in the world, 500 meters long, with massive gates shipped in from South Korea. Building a giant ship lock is one of the hardest engineering jobs on the planet. Watch through to see a 3,285-ton steel gate rolled into place on 400 wheels. Every ship crossing the Panama Canal, from a sailboat to a massive cruise liner, gets lifted 26 meters above sea level by nothing but water. Control operators close the gates and open valves. The chamber fills in 8 minutes. The whole ocean-to-ocean transit takes 8 to 10 hours. Now put yourself on board. The M.V. Canadian Olympic sits inside Lock 6 of the Welland Canal as turbulent water floods in around the hull. Seagulls circle overhead. The gates close behind the ship, water levels shift, and the gates ahead swing open. A bathtub big enough to swallow a cargo ship. The Welland Canal is 42 kilometers of engineering that lets ships climb around Niagara Falls without going over it. From Port Colborne on Lake Erie to Port Weller on Lake Ontario, vessels crawl through lock after lock, rising the height of the Niagara Escarpment. Time-lapse cameras compress hours of transit into minutes. Bridges lifting, concrete walls sliding past, industrial shorelines stretching into dusk, all to spare shipping companies the small inconvenience of a 51-meter waterfall. Then the truly big ships arrive. The Norwegian Bliss, 325 meters long, 41 meters wide, 168,000 gross tons, and nearly 5,000 passengers, became the largest cruise ship to ever transit the expanded Panama Canal. Slotting a floating city into a concrete box demands the kind of tolerance most people cannot picture. Which explains why the expansion was called the biggest engineering job of the decade. The Panama Canal's third set of locks required 50 million cubic meters of excavation, 5 million cubic meters of concrete, and 290,000 tons of steel, with roughly 10,000 workers on site every day. Each new lock has 3 chambers, 55 meters wide, 427 meters long, and 18 meters deep. That is enough space to fit a building the size of the Empire State Building lying on its side inside a single chamber. Each lock gate weighs over 4,000 tons and slides open in under 5 minutes, an operation that repeats dozens of times a day, every day of the year. Una nueva experiencia, ampliación del Canal de Panama. Content on this same expansion project dimensions, water-saving basins, operating procedures fits cleanly here, so we cover it under this link and skip a repeat listing. And still, the whole system saves 60% of the water on every transit through recycling basins. A 5,000-passenger ship climbing 26 meters, and the water gets a second and third chance to do the same job. Before a shovel touches dirt, someone has to know exactly what is under the water. Hydrography crews at the Panama Canal run bathymetric surveys 24/7 using sonar and GPS. Their job is to be the eyes below the surface, mapping the seabed and flagging what would otherwise sink a ship. And when the site is entirely underwater, the measuring tape gets a lot more expensive. And ROVE, a remotely operated vehicle, sets acoustic transponders called compats inside seafloor structures like plet hubs and manifolds. Precise measurements get taken between compats to the millimeter, The rove rotates each compad in 90-degree increments to eliminate error. Then the seafloor gets profiled between the 2 points using pressure sensors called digicords. That data becomes the exact blueprint for fabricating a connecting jumper on the surface. Get the survey wrong, and you fabricate a very expensive metal shape that fits absolutely nothing. Then comes the ongoing job of clearing what the survey found. The Panama Canal's dredging fleet includes cutter suction dredges and mechanical bucket dredges dating back to 1943, running around the clock to fight landslides in the Culebra Cut and maintain over 1,500 modern channel markers. Cross-section the whole Panama Canal expansion program at once. 2 lock complexes, a raised Gatun Lake level, deeper navigation channels at both entrances, dredging and widening of Gatun Lake, deepening of the Culebra Cut, and a brand new 6.1-kilometer Pacific Access Channel, all executed in parallel. Now watch how a modern megalock gets built from scratch. At Ajimuiden in the Netherlands, crews replaced a 1929 lock with the largest sea lock in the world. 500 meters long, 70 meters wide, and 18 meters deep. The build started in 2016 with excavation, digital modeling in 3D, and lock gate fabrication over 8,000 kilometers away in South Korea. No way. The gates got shipped that far across the ocean just to reach the site. The gates were then maneuvered into position by tugs. Concrete plants, solar panels, and a full control center all came together over 6 years to open the lock in 2022. This is one of the most complex construction jobs of the last decade. 6 years of work most people never watched happen. Drop a comment below telling me which megalock project fascinates you most, Panama, Ijemuiden, or something else entirely. Excavation for a lock is not just digging. It is controlled destruction on an industrial scale. 5 years into the Panama Canal expansion, controlled explosions rocked the site while dump trucks and excavators hauled millions of cubic meters of rock away, with 26,636 direct jobs feeding the workforce. And when the pit walls are 50 meters tall, keeping them from collapsing becomes a mountaineering job. Panamanian alpinists rappel down the excavation walls at the new Panama Canal locks, installing safety mesh capable of stopping rock falls before those rocks find the workers below. Germany went even bigger. At the Kriegenbrunn lock replacement on the main Danube Canal, the main excavation pit runs 330 meters long, 30 meters wide, and almost 30 meters deep, secured by overlapping board piles up to 2 meters in diameter, plus 8,000 tons of steel bracing. On the Ijemuiden project, the answer to keeping the pit walls stable was diaphragm walls. Crews used low-vibration grabbing equipment to dig 1.3-meter thick concrete walls reaching 35 meters below sea level. 80,000 cubic meters of underwater concrete poured while the old lock next door kept operating. Sometimes the entire pit has to be built floating. At Great Yarmouth Harbor, crews had 3 months to install 2 circular cofferdams, enclosures that hold water back so the crew can work in a dry chamber. At the harbor breakwaters, with almost zero disruption to shipping, the solution was to pre-assemble the cofferdams onshore first. Straight web sheet piles were interlocked around a temporary support frame. Then a shear leg crane barge lifted the whole 400-ton structure and floated it into position using GPS. Vibratory hammers drove the piles into the seabed, a construction project that showed up by boat. The technique behind those cofferdams comes down to a single principle. You can build a dry room in the ocean if you close it tight enough. Cellular cofferdams use straight-web steel sheet piles interlocked into circular cells. Each cell essentially a giant steel drum sunk into the seabed and then filled with sand. The build sequence starts with a guiding frame positioned exactly where the cell needs to go. Sheet piles get driven around it one by one, forming the circular wall. Once the ring closes, the interior gets pumped full of sand. That sand load presses outward on the interlocked piles, but the geometry converts that pressure into pure tension in the steel, which the interlocks are engineered to handle without leaking or deforming. Each cell becomes a self-supporting island. String enough cells together and you get a complete waterfront structure. A ferry terminal, a lock wall, a dry dock, sitting where there used to be open water. A wall of steel drums standing in the ocean, holding it back with nothing but interlocking hooks and physics. The final steps are dredging the interior, laying the terminal deck, and adding lighting, paving, and berthing gear. What was open sea becomes working infrastructure. Then, back to diaphragm walls at scale. At the new lock in Terneuzen, crews poured 125 diaphragm walls down to 45 meters below sea level. Bentonite slurry, holding the trench open while rebar cages get lowered and concrete gets pumped in, one 7.5-meter panel at a time. Once the pit is dug and the walls are holding, the real construction begins. At the Panama Canal expansion, dump trucks the size of two-story buildings crawl through the site while dozens of cranes rise over freshly poured concrete walls. Workers pour foundations, tie rebar over hundreds of tons of steel, and prep formwork for the next lift. The pit alone was a small mountain worth of removed rock, and now the mountain gets rebuilt in concrete. Aerial shots make it clear this is not one job. It is dozens of parallel jobs happening at the same time. Now the numbers start getting personal. Over 35,000 workers had poured more than 3 million cubic meters of concrete and excavated 38 million cubic meters of earth and rock at the Panama Canal expansion site. Basalt rock got quarried from the Pacific side and hauled 80 kilometers north by barge, 40,000 tons a week, to feed the concrete plants on the Atlantic side. Each plant had its own grinding, storage, and rebar cutting industrial park. Say you had to keep an 8,000-person site fed with the right rebar, cement, and formwork every day for years. Would you rather run the logistics or run the concrete pour? Now move to IJmuiden. A time lapse from July to September 2017 shows the site at a completely different phase. Earth-moving equipment carving out the excavation while diaphragm walls take shape and formwork rises for the first concrete lifts. Aerial drone shots reveal simultaneous construction across the whole site. Inner gate chambers getting concrete pours, wall anchors being drilled and installed, an intermediate dam protecting the work zone, and a lock operations center rising alongside. The western spit doubles as a sand depot. Concrete gets poured for the southern lock entrance walls at the seaside. Every element has to interlock in sequence, because the site is one massive assembly with no room to shuffle. Skip one dependency, and half the site sits idle waiting for it. A single quarter of drone footage tells the story. In Q3 of 2020, IJmuiden crews were building the quay wall and inner harbor, welding rebar for concrete structures, running a cutter suction dredger inside the lock chamber, and sending divers underwater to work on the lock sill. The site ran through day-to-night time lapses under artificial lights, with excavators placing rocks on the western land tongue and dredgers spraying sand and water mixtures underwater. Man, 3 months of footage and the site never actually stopped moving. A lock gate is not something you weld together in an afternoon. For the new Panama Canal gates, workers moved massive steel plates with forklifts and magnetic lifters, sliced them with plasma cutters throwing bright sparks, and assembled the frames under gantry cranes running multiple automated welding heads at once. Blueprints get consulted between every step. Surveyors measure the growing structure with total stations. Then the finished modules ride heavy-duty transporters and eventually a barge across the Atlantic. Every one of these gates is basically a small building lying on its side. A time-lapse of a segment door being built for Sluis Eefde in the Netherlands shows steel structure supported by wooden blocks, growing outward through welding and grinding. The first segment door for a lock chamber this size in the country. On the Nieuwe Sluis project in the Netherlands, the gates and bridges got built in China. 10,000 tons of steel went into 4 lock doors, each 58 meters long, 25 meters wide, 9 meters deep, plus 2 bascule bridges 84 meters long. Then heavy-duty transporters rolled the modules out of the workshop. Every rolling gate needs track wheels. A giant metal shaft gets machined on a lathe with coolant flowing over the cutting tool. Precision holes get drilled. Workers assemble the finished track wheel components, parts that will carry thousands of tons of steel across the bottom of a lock chamber for decades. Now watch a gate arrive. Barges carrying modular lock gate sections come into port assisted by tugboats. Multi-story steel sections then get transferred to heavy-duty trailers with hundreds of wheels for the final journey to the installation site. Heavy-haul trailers crawl through the site, carrying gate sections that dwarf the trucks pulling them. Barges nudged by tugboats maneuver more sections through the water at sunset, silhouettes of towering steel against the sky. When your delivery truck has 400 wheels, you know the cargo is not ordinary. In Belgium, the Kieldrecht lock installation involved 12,000 tons of steel across 4 lock gates and 2 bascule bridges. Submersible vessels delivered the components. Pontoons unloaded them. Massive cranes toppled gates into the water. Then tugboats maneuvered them into position with almost no clearance to spare. Land-based transport handled the bridges, self-propelled heavy-lift transporters rolling entire bridge sections into their final resting spots. Then the actual install. Self-propelled motorized wheel transporters with over 400 wheels rolled a 3,285-ton gate, 30 meters tall, 10 meters wide, into position in one of the new Panama Canal chambers. In total, 16 rolling gates went in, 8 on the Pacific, 8 on the Atlantic. Sometimes the crane approach is more elegant. At Sluis Eefde in the Netherlands, a heavy-lift crane hoisted a segment door between 2 scaffolded support towers. Then barges and tugboats brought a matching lock gate to be lowered into position. Even routine gate swaps are heavy work. A crane barge lifted the spare Kramersluizen gate, 26 meters long, 12 meters tall, weighing 340,000 kilograms, from the shore onto a pontoon for transport. Multiple tugboats worked around the barge while wind turbines turned in the background. And when a gate goes back on its hinges after renovation, it looks almost effortless. Two cranes on a barge at Sluice Wirt lifted a large blue gate horizontally over the lock, tilted it vertically, and lowered it precisely into its mounting position. A maneuver measured in centimeters. Every giant lock is really a giant water management system. At the new Panama Canal, each lock chamber has 3 water-saving basins, each about 70 meters wide and 5.5 meters deep, that reuse 60% of the water on every transit and cut water use by 7% compared to the old locks. Different gates handle different jobs. Floating caisson gates plug chambers for dry maintenance. Miter gates, the original 110-year-old designs, still work at Miraflores. Vertical displacement gates at the Gatun and Miraflores dams release water to prevent flooding. By early 2016, the Panama Canal expansion was in its testing phase. Between December 2014 and April 2015, all 16 rolling gates were inserted into the Cocali and Agua Clara locks. Then 152 valves controlling water flow between chambers, the lake, and the water-saving basins got installed. The chambers were flooded to test gate operation. Water-saving basins started their own filling and pressure tests. Concrete pours totaled 4.4 million cubic meters. Control systems from every subsystem, hydraulic, mechanical, electrical, had to be integrated into one operating whole. How many valves are we talking about? 152 for water flow control alone, and every one has to open and close on command without failing. Tell me below, would you rather be the engineer who signed off on the last valve or the crew that installed the first one? Dams got built on the Pacific side to hold the water level in the new approach channel, one of them 2.3 kilometers long, separating the new channel from the existing one. Now compare that to what modernization looks like in India. The new navigational lock at the Farakka Barrage on National Waterway 1 combines miter gates, caisson gates, bulkhead gates, and radial gates in one electromechanical hydraulic automated system. The old 1987 lock took nearly 2 hours per vessel crossing. The replacement, built for 375 crore rupees with World Bank support, cut that time to 23 minutes. Remote operation runs from a central control room, and both locks will eventually operate in parallel for simultaneous crossings. Whoa, that is a 5x throughput jump from a single upgrade. Ship locks do not exist in isolation. They depend on the reservoir above them. During rainy season, the Panama Canal monitors Gatun and Alajuela lake levels 24/7. When water approaches maximum operating levels, preventive spillway releases at the Gatun and Madden dams protect surrounding communities. The final tests start with water, and lots of it. The water-saving basins at the new Panama Canal locks were pumped full for the first time to check structural integrity of the filling and emptying system, delivering the 60% water savings the design promised. A walking tour through the finished lock chambers hits different. Ground-level shots inside the new Panama Canal chambers reveal the sheer verticality. Concrete walls rising higher than any building most viewers have walked next to, echoing corridors that will soon hold ships instead of workers. Then the gates get tested with real ships. At the world's largest sea lock in IJmuiden, tankers like the Petrol Pacific and Torm Amelie ran controlled test transits, measuring mooring line forces during freshwater and saltwater exchanges as the gates opened. Sometimes a full year of the Panama Canal expansion fits into 60 seconds. Time-lapse compilations catch the earth moving, concrete pouring, wall construction, and gate installation all in one flowing sequence. Post-Panamax container ships transiting the finished section appear at the end. Comparison of Panamax versus Neo-Panamax capacity, making the whole point of the project visible in a single frame. Within 2 years of the Panama Canal expansion opening, transits exceeded projections. Container ships, LNG tankers, up to 3 in a single day, and the largest cruise ships in the world all made their inaugural passages through the new locks. One transit tells the whole story. The Cotrotter from Oslo, one of the largest car carriers in the world with capacity for 8,500 vehicles, enters the Agua Clara locks. In fiscal 2018 alone, 834 Panamax and Neo-Panamax vehicle carriers used the canal, a historic record. And then the cruise ships arrived by the fleet, the Carnival Spirit, with capacity for 2,680 passengers, kicked off the 2022 to 2023 season with over 200 expected transits, including 44 Neo-Panamax vessels and inaugural passages for 12 different ships. And then the finished shot from the sky. Aerial views of the expanded Panama Canal show completed lock structures, dredging operations still running for maintenance, and one massive container ship transiting through the new channel. 8 years of construction summarized in a single frame. A ship lock is not really about moving ships. It is about controlling the boundary between two bodies of water at different levels, and doing it thousands of times without ever spilling one into the other, which is exactly why automation, remote operation, and AI-assisted lock scheduling are becoming increasingly important. Global shipping keeps pushing for larger vessels, shorter transit times, and more efficient use of water, all at the same time. With sea levels rising and shipping traffic growing, is the age of the megalock reaching its natural ceiling? Or are we just getting started? What do you think? Comment below. Hit that subscribe button if you want more deep dives into how massive infrastructure actually gets built. The next one is already on the way. See you. Take care.